A thermocouple is an electrical device consisting of two different conductors forming electrical junctions at differing temperatures. A thermocouple produces a temperature-dependent voltage as a result of the thermoelectric effect, and this voltage can be interpreted to measure temperature. Thermocouples are a widely used type of temperature sensor. Commercial thermocouples are inexpensive, interchangeable, are supplied with standard connectors, and can measure a wide range of temperatures. In contrast to most other methods of temperature measurement, thermocouples are self-powered and require no external form of excitation. The main limitation with thermocouples is accuracy. System errors of less than 1 degree Celsius can be difficult to achieve. Thermocouples are widely used in science and industry. Applications include temperature measurement for kilns, gas turbine exhaust, diesel engines, and other industrial processes. Thermocouples are also used in homes, offices and businesses as the temperature sensors in thermostats, and also as flame sensors in safety devices for gas-powered major appliances. Principle of operation. In 1821, the German physicist Thomas Johann Seebeck discovered that when different metals are joined at the ends and there is a temperature difference between the joints, a magnetic field is observed. At the time, Seebeck referred to this as thermomagnetism. The magnetic field he observed was later shown to be due to thermoelectric current. In practical use, the voltage generated at a single junction of two different types of wire is what is of interest, as this can be used to measure temperature at very high and low temperatures. The magnitude of the voltage depends on the types of wire used. Generally, the voltage is in the microvolt range and care must be taken to obtain a usable measurement. Although current flows, very little power can be generated by a single thermocouple junction. Power generation using multiple thermocouples as in a thermopile is common, though the standard configuration for thermocouple usage is shown in the figure. Briefly, the desired temperature sense is obtained using three inputs: the characteristic function E of the thermocouple, the measured voltage V, and the reference junction's temperature TREF. The solution to the equation E equals V plus E yields sense. These details are often hidden from the user since the reference junction block, voltmeter, and equation solver are combined into a single product. Physical principle. Seebeck effect. The Seebeck effect refers to an electromotive force whenever there is a temperature gradient in a conductive material. Under open circuit conditions where there is no internal current flow, the gradient of voltage, whereas a temperature-dependent material property known as the Seebeck coefficient. The standard measurement configuration shown in the figure shows 4 temperature regions and thus 4 voltage contributions. Change from 2 in the lower copper wire, change from 2 in the aluminum wire, change from 2 in the chromel wire, change from 2 in the upper copper wire. The first and fourth contributions cancel out exactly, because these regions involve the same temperature change in an identical material. As a result, does not influence the measured voltage. The second and third contributions do not cancel, as they involve different materials. The measured voltage turns out to be where and are the Seebeck coefficients of the conductors attached to the positive and negative terminals of the voltmeter, respectively. Characteristic function. An integral does not need to be performed for every temperature measurement. Rather, the thermocouple's behavior is captured by a characteristic function, which needs only to be consulted at 2 arguments. In terms of the Seebeck coefficients, the characteristic function is defined by the constant of integration. In this indefinite integral has no significance, but is conventionally chosen such that thermocouple manufacturers and metrology standards organizations such as NIST provide tables of the function that have been measured and interpolated over a range of temperatures. For particular thermocouple types, requirement for a reference junction to obtain the desired measurement of it is not sufficient to just measure the temperature at the reference junctions must be already known. 2 strategies are often used here. Ice bath method. The reference junction block is immersed in a semi-frozen bath of distilled water at atmospheric pressure. The precise temperature of the melting point phase transition acts as a natural thermostat, fixing to 0 degrees Celsius. Reference junction sensor. The reference junction block is allowed to vary in temperature, but the temperature is measured at this block using a separate temperature sensor. This secondary measurement is used to compensate for temperature variation at the junction block. The thermocouple junction is often exposed to extreme environments, while the reference junction is often mounted near the instrument's location. Semiconductor thermometer devices are often used in modern thermocouple instruments. In both cases, the value is calculated, then the function is searched for a matching value. The argument where this match occurs is the value of. A less common strategy is to use a hot reference junction. Historically, this was commonly found in temperature-critical processing plants where large numbers, often in the hundreds, of thermocouples were installed. It permitted the wiring from the field to the instrumentation or control room be done using copper cable. Temperature control of the hot reference was either by an electrically heated, precision RTD-controlled system or occasionally by a bimetallic-controlled steam heater. Practical concerns. Thermocouples ideally should be very simple measurement devices, with each type being characterized by a precise curve, independent of any other details. In reality, thermocouples are affected by issues such as alloy manufacturing uncertainties, aging effects, and circuit design mistakes, misunderstandings. Circuit construction. The most common error in thermocouple construction is a circuit extension with dissimilar metals such as copper wires. As explained in the principles section above, it is crucial to know the temperature at this point of transition, as this point is the very definition of the reference junction. All further junctions are irrelevant past the point where the switch to copper is made. The mistake is in making this junction without measuring its temperature, and then proceeding as if the reference junction is a different junction nearer the voltmeter, when the compensated voltage is calculated. This fake reference's temperature is used in place of the actual reference temperature. If the desire is to make an extension without needing a thermometer at that location, then extension wire may be used. This allows the reference junction to be made closer to the voltmeter. Junctions should be made in a reliable manner, but there are many possible approaches to accomplish this. For low temperatures, junctions can be brazed or soldered. However, it may be difficult to find a suitable flux, and this may not be suitable at the sensor junction due to the low solder melting point. Reference and extension junctions are therefore usually made with screw terminal blocks. For high temperatures, a common approach is a spot weld or crimp using a durable material. A common myth regarding thermocouples is that junctions must be made cleanly without involving a third metal, to avoid unwanted added EMFs. This may result from another common misunderstanding that the voltage is generated at the junction. In fact, the junctions should in principle have uniform internal temperature, therefore no voltage is generated at the junction. The voltage is generated in the thermal gradient along the wire. A thermocouple produces small signals, often microvolts in magnitude. Precise measurements of this signal require an amplifier with low input offset voltage and with care taken to avoid thermal EMFs from self-heating within the voltmeter itself. If the thermocouple wire has a high resistance for some reason, then the measuring instrument should have high input impedance to prevent an offset in the voltage measured. A useful feature in thermocouple instrumentation will simultaneously measure resistance and detect faulty connections in the wiring or at thermocouple junctions. Metallurgical grades. While a thermocouple wire type is often described by its chemical composition, the actual aim is to produce a pair of wires that follow a standardized curve. Impurities affect each batch of metal differently, producing variable Seebeck coefficients. To match the standard behavior, thermocouple wire manufacturers will deliberately mix in additional impurities to dope the alloy. compensating for uncontrolled variations in source material. As a result, there are standard and specialized grades of thermocouple wire, depending on the level of precision demanded in the thermocouple behavior. Precision grades may only be available in matched pairs, where one wire is modified to compensate for deficiencies in the other wire. A special case of thermocouple wire is known as extension grade, designed to carry the thermoelectric circuit over a longer distance. Extension wires follow the stated curve, but for various reasons they are not designed to be used in extreme environments, and so they cannot be used at the sensing junction in some applications. For example, an extension wire may be in a different form, such as highly flexible with stranded construction and plastic insulation, or be part of a multi-wire cable for carrying many thermocouple circuits. With expensive noble metal thermocouples, the extension wires may even be made of a completely different, cheaper material that mimics the standard type over a reduced temperature range. Aging of thermocouples. Thermocouples are often used at high temperatures and in reactive furnace atmospheres. In this case, the practical lifetime is limited by thermocouple aging. The thermoelectric coefficients of the wires in a thermocouple that is used to measure very high temperatures may change with time, and the measurement voltage accordingly drops. As thermocouples age in a process, their conductors can lose homogeneity due to chemical and metallurgical changes caused by extreme or prolonged exposure to high temperatures. If the aged section of the thermocouple circuit is exposed to a temperature gradient, the measured voltage will differ, resulting in error. Aged thermocouples are only partly modified, for example being unaffected in the parts outside the furnace. For this reason, aged thermocouples cannot be taken out of their installed location and recalibrated in a bath or test furnace to determine error. This also explains why error can sometimes be observed when an aged thermocouple is pulled partly out of a furnace, as the sensor is pulled back. Aged sections may see exposure to increased temperature gradients from hot to cold as the aged section now passes through the cooler refractory area, contributing significant error to the measurement. Likewise, an aged thermocouple that is pushed deeper into the furnace might sometimes provide a more accurate reading if being pushed further into the furnace causes the temperature gradient to occur only in a fresh section.